Hi, I'm Dr. Roji. In this session, we'll see the types of semiconductor, the most important semiconductor device, the MOSFET, the working of the MOSFET, the regions of operation of the MOSFET, and finally, we'll end with the current equation derivation of the MOSFET.
Silicon and germanium are the commonly used semiconductors. They belong to the group 4 category of elements. The slide shows you the periodic table. A pure semiconductor or an intrinsic semiconductor is one which does not have any impurity atoms. The process of introducing foreign atoms into a semiconductor material is called doping. When an intrinsic semiconductor is doped, its electrical properties change and it becomes an extrinsic semiconductor. Group 3 and group 5 elements are normally used as dopants. the voltage VGS is increased further, more electrons are induced at the surface. The substrate is of p-type, but the surface has become n-type. So can we say that the type of the surface is inverted? The operation in this region is called the inversion region. In the last session, we saw some basics of MOSFET. The three terminals of the MOSFET are the gate, drain, and the source. So the three terminal voltages are VG, the gate voltage, VD, the drain voltage, and VS, the source voltage. The three terminal voltages can be combined to form the potential difference between any two terminals. For example, the potential difference between the gate and the source is VGS. So VGS can be written as VGS is equal to VG minus VS, which is equation number 1. The potential difference between the gate and the drain is VGD. So VGD becomes VG minus VD, which is taken as equation number 2. So VDS is the potential difference between the drain and the source. So VDS is equal to VD minus VS, which is equation number 3. By combining equations 1 and 2, we get VDS is equal to VGS minus VGD. A quick recap on the different operating modes of a MOSFET: the accumulation, cutoff, depletion, and the inversion region. First, we'll see about the accumulation region. In all our discussions, we concentrate mainly on the N-channel MOSFET. The substrate of the N-channel MOSFET is of p-type. So, when more holes accumulate at the surface, we call this as the accumulation region. And this happens when Vg is less than 0. The next mode of operation is the formation of the depletion region. The depletion region occurs when the surface is depleted of all mobile carriers. This occurs when Vg is less than Vt and greater than 0. So what is this Vt? Vt is the threshold voltage. It is defined as the minimum gate to source voltage needed to form a conducting path between the source and the drain terminals. The conducting path is nothing but the channel. So threshold voltage is also the minimum VGS needed to form a channel. The last mode of operation is the formation of the inversion region. This occurs when Vg is greater than Vt. The condition implies that the channel has been formed. So where is the channel? The channel consists of the electrons which were induced at the surface. So based on the knowledge of the different operating modes, the MOSFET can be either in the off state or in the on state. When it is in the off state, it is said to be cut off. And when it is in the on state, it can be either in the linear region or in the saturation region. By carefully choosing VGS and VDS, the MOSFET can be made to work in any of the above operating regions. VGS is responsible for the vertical electric field and VDS forms the horizontal electric field. So when you keep both VGS and VDS at 0, the MOSFET is said to be off. There will be no channel and the drain to source current is 0. When VGS is kept at a voltage slightly above the threshold voltage, the channel is formed. Now apply a small VDS. The electrons in the channel start to move from the source to the drain. When a MOSFET operates in this region, it is called the linear region. It's because the current has a linear increase with VDS. This is also called the ohmic region. The reason is the voltage VDS changes with IDS in the same way as the voltage across a resistor would change with current. So we call it as the ohmic region. So what should be the different voltages to keep the MOSFET in the linear region? The first condition should be VDS is small. VDS should be smaller than VGS minus VT. Rearranging the equation, we get VDG should be less than minus VT, which yields VGD should be greater than VT. VDS should be small to keep the MOSFET in the linear region. But if it is too small, it will turn off the MOSFET. So VDS should be greater than 0. We can split VDS as VDG plus VGS. VDG can be rewritten as minus VGD. So VGS minus VGD should be greater than 0, which yields VGS should be greater than VGD. So the two essential conditions for the MOSFET to be in the linear region are VGD should be greater than VT and VGS should be greater than VGD. As VDS is increased, the channel starts to constrict near the drain end. The channel region has been shown separately now. The channel constricts, and if you still continue to increase your VDS, the channel becomes a point at the drain end, which is called the pinch-off region. The operation in this region is called the saturation region. So beyond the pinch-off point, the current is constant, irrespective of any changes in VDS, or IDS is independent of VDS. Can we say that the current has saturated? That's why this region is called the saturation region. As in the case of linear region, we'll derive the voltages for operation in the saturation region. Unlike the linear region, for the operation to be in the saturation region, the main condition is VDS should be large. How large should it be? It should be greater than VGS minus VT. So VDS minus VGS should be greater than minus VT, which gives us VDG should be greater than minus VT, or VGD should be less than VT. So far, we have discussed how the drain to source current will change. When it is in the linear region, it will increase with VDS, and when it is in the saturation region, IDS will be constant irrespective of any changes in VDS, and when the operation is in the cutoff region, IDS will be 0. Now, we'll go ahead and derive the IV characteristics equation. So, IDS depends upon charge in the channel and speed of the carriers. First, we'll derive an expression for the speed of the carriers. The carriers move in the channel. They start from the source and they move towards the drain. So the carriers cover a length of capital L, and the lateral electric field VDS is responsible for the movement of these carriers. So the carrier velocity V is mu into E. Mu is the mobility and E is VDS by L. So V becomes mu into VDS by L, which is taken as equation number 6. So the time taken for the carriers to cross the channel whose length is L is T is equal to L by V. We have got the expression for V in equation number 6. Substitute this, we get T is equal to L squared divided by mu into VDS. The channel charge density is equal to the gate capacitance times the gate voltage in excess of the threshold voltage, or VGC minus VT, where VGC is the average gate to channel potential and VT is the threshold voltage. Gate capacitance is epsilon aux WL by T aux. Remember, W is the width of the transistor as was seen in one of the previous slides. Epsilon aux, permittivity of silicon dioxide. T aux is the thickness of gate oxide. Epsilon aux by T aux gives C aux. Another important parameter needed to calculate IDS is VGC, which is the average gate to channel potential. VGC is the average of VGS and VGD. Doing the calculation, we finally get VGC is equal to VGS minus VDS by 2. When we started the derivation of IDS, We said that IDS is dependent upon the charge in the channel and speed by which the carriers cross the channel. So IDS will be equal to Q channel by T. We have got the expression for Q channel. Q channel is C into V. V is VGC in excess of VT. In this session, we have derived VGC, C, and T. Substituting them in the equation for IDS, IDS becomes mu Cox WL by T into VGS minus VT minus VDS by 2. Mu Cox WL by T is combined as beta. Beta should never be confused with the transistor current gain. Here, in the case of MOSFET, beta is a technology and geometric parameter. So we have derived the current equation for the MOSFET in the linear region. That has to be modified for the saturation region. For this, we should substitute the conditions for saturation, which are VGD should be less than VT, VDS should be large, and it should be greater than VGS minus VT, and the MOSFET goes into the saturation when VDS is greater than VD sat. And we have also seen that in the saturation region, IDS is constant. So applying all these in equation 16, we get IDS is equal to beta into VGS minus VT the whole square divided by 2. This is the equation for the current in the saturation region. We have come to the end of another session. Thank you.